At this point, I just want to know if there are any questions. I wanted you to ask, there will be lots of time for questions later, but I also want to make sure there are any clarifying questions get asked along the way. You know, a whole bunch of questions. Yes?
I noticed in your key you had a symbol for astrometry and then that went away.
Yes, it wasn't on purpose, but let me see. You know, actually, maybe it was. It was one of those, you know, Freudian slopes.
Was there any discovered by astronomy?
Well, that's a good question. And astronomy has a very checkered history for exoplanets. Traditionally, had found some around Barnard star that went away. And more recently, one was also announced around a star called VB10. And it was not verified by a different technique, rate of velocity. I'm not sure if the original authors retracted it, but the community doesn't believe it exists yet until more evidence is presented. So I would say safely that astronomy has not yet produced robust evidence for an exoplanet. But like everything, you know, people are investing, and this one will come to fruition eventually. And we'll find planets in slightly different parameters. Okay, I'll just take maybe, I shouldn't have said questions, now we'll have a huge number of questions, but I'll take one more question now, unless it's a worrying question. Oh, good question. What is this line? Okay, first of all, there actually, let me see if I remember to put, yes, I did. Do you see Pluto there? Pluto's at the bottom. Doesn't really fit on the graphic, it's so small. Actually, Pluto did go away on purpose, because Pluto is no longer considered a planet. This actually, you know, actually this is a disgrace to science. Because you know how Pluto got demoted? By voting. Science should not be a voting process. And so this raises a lot of issues. There's a lot of politics involved in this story. But actually, you know, for anyone who loves Pluto, don't worry, because we still love Pluto. And we hope that things will resolve, that we actually, sort of in the community now, we just want to use it as a way to describe the solar system in a new way. It's not just the 8 major planets, we also have the dwarf planets. And I'm not kidding, all these discussions, like, is a dwarf planet a planet? Well, is a teddy bear a bear? It's crazy what's going on. But so there are a lot of interesting things in the solar system, the asteroids, there's dust, et cetera, et cetera. Okay, so Pluto went away. But in exoplanets, we don't argue about small things because we can never detect them. And exoplanets is a different argument because people love to argue. And they're arguing about the big things. What do you call a planet? What is a planet? What is not a planet? And that line up there is the line above which astronomers have, in sort of arbitrary way, agreed that there are not planets above there. But I put it on because I didn't discriminate when I made these plots. You can see the planets seem to have a natural cutoff on their own, right? And what that line is, people would like to say that a star creates energy on the inside, it fuses hydrogen and deuterium, but planets do not. And so how would you define this? Would you say a planet doesn't fuse a single atom of deuterium? How would you know? Well, it has to do with the mass and what the planet is made of exactly. And it's not really clear. That line for the astronomers in the room was just made for 50% deuterium burning for solar metallicity object. So I put it there to just sort of tell you about the debate exoplanet people have, and also to show that nature gave us a different definition, which I might actually take instead. Okay, so discover this, to summarize this part of the talk. Hundreds of exoplanets are known. Monumental exoplanet achievements were made despite the widespread skepticism. And the huge promise for the future is based on achievements in the past 2 decades. And I only put that summary that way because later in the talk and in the next talks, some things I say might seem way out there to you. But I believe because of the past history and that other people spent 15 years in obscurity believing in something that was within technological reach, these other things will also happen. And you'll see where I'm getting later. Now I'm going to talk about discovery phase 2. Ultimately, what we'd like to do is find a planet like Earth and do direct imaging where we take an image of that planet. And as I mentioned earlier, we're not going to get that beautiful spatially resolved image like the Apollo images of Earth, but we will have a point source. Now, an Earth planet, an Earth-like planet, not within that red bubble that I showed earlier, is not too faint. You know, it's not fainter than the faintest galaxies ever observed by the Hubble Space Telescope. The problem is it's right next to a very bright star. And the analogy that we have in exoplanets is that it's like looking for a firefly right next to a searchlight, when that firefly and searchlight is about 2,400 miles away. That's like between here and Los Angeles. It's very far. Imagine trying to see not just the searchlight itself, but the planet. Now, this picture is from National Geographic, and a number of years ago I was consulting for them. And it was my job to comment on the pictures that they took or the illustrations they made and see how accurate they were. And I have to say that the National Geographic writers and artists were pretty much among the smartest people I've ever met. What they did was, that I was unhappy with, I said something good so I could say something negative, but I was unhappy with it, was they actually wanted to take the real picture. And they rented the searchlights and put it in a field somewhere in Maryland. I didn't like how they, see, you know how searchlights come all together like this? Because stars are not like that. You don't have stars, all four of them, like attached to each other. That I didn't like. But here they have this. You can see the firefly here. And the Earth, compared to the sun at visible wavelengths, is extremely faint. It's actually 10 billion times fainter. And for the non-scientists here, because we're used to dealing with these really huge numbers, but let's think about that for just a couple of seconds. And a good way to think about it is in terms of money. What can you buy for $1? If I went on campus to the local Starbucks in this building, I mean, could I even buy coffee? I don't think so. Can't buy too much. But what about if I had $10 billion? That's a lot. I mean, that's a huge, huge, huge number. That's the difference in brightness between Earth and the sun. So the problem is you have to get rid of that starlight at 1 part in 10 billion, and that will be my talk, part of the talk tomorrow. All right, so they couldn't take this picture, okay, because we can't do this in exoplanets. They couldn't take the picture. They punched the firefly there. You can see it's almost as bright as the star. But what they were so clever about is they came back and they were so excited. They said, we could do this picture. You know what we could do? We could do it when the firefly is in front of the star, blocking out light from the star. And this is very relevant to the rest of my talk, because that's what we're able to do, actually, in exoplanets. The part where you want to see that Earth on its own without the stars, 1 part in 10 billion. The transit Earth, when it goes in front of the star and blocks out light, it's related to the ratio of the areas of the planet to star. That's a part in 10,000. Now back to the money analogy, for 10,000 you can still buy a lot more than 1 coffee. So 1 in 10,000 is still very difficult, no matter what science field you're in, a very difficult measurement to make that precision, but it's much easier than 1 part in 10 billion. So now here's a little movie showing you a transiting planet. Can you see the transiting planet on that sun-like star? It's really hard to see, it's really tiny. That's how Earth would be seen from far away in front of the sun. And remember, I told you we can never spatially resolve even a star like this. They're all built by point sources. This is showing you the graph of what we will measure and what we measure for exoplanets. The star is relatively constant with time, and then it drops in brightness in ratio to the planet to star area, and then it returns to normal. And this here is just showing noise from the star itself, or perhaps in the measurement process. So the big thing that's happening in exoplanets, and why I call it phase 2 discovery, is the Kepler Space Telescope. It's NASA's telescope. It was the first one designed only for exoplanets, and it launched March 6, 2009. It's a 1 meter aperture. Kepler is looking at 150,000 stars for over 3 years, looking for transiting Earth-sized planets. I was at the launch. It was the first and only launch I've ever been to. And it was really quite an amazing time. First of all, we had a science team meeting in the days leading up to the launch. And it was a little tight because the week before, a carbon dioxide satellite had failed to launch and actually gone into the ocean. And if that happens, they're going to be super, super careful about any following launch. Even though it was a different launch vehicle, it only had 1 part in common. And it took a time to review and see whether that part was at fault, even though it was like 1 part out of probably 1,000 different parts. And it turned out that particular part had worked hundreds of times and there was no problem. So it took a day, and then that was all clear to go. And I remember how amazing the night was. It was a very clear night. We were with all of the official people with Kepler, and it was a night launch around 11 o'clock at night. And on the field where we were, there were all sorts of people who had been with the mission for a decade or more. There were children running around. It was quite a time. And then it was ready for launch. And the countdown on the speakers, it was exactly like in the movies, with the movie voice counting down. And then it launched perfectly. And what was really amazing was when it launches, the booster rockets fall off, and they're so hot, you can see them glowing. And they're dangling down. They end up falling in the ocean to be retrieved later. And that thing launched perfectly, went off into orbit, got it there, and is doing a fantastic job for exoplanets. So Kepler is up there, and what it's going to do is determine the frequency of Earth-sized planets in the so-called habitable zone of the star. That is just an Earth-like orbit. I'll come back and talk about habitable zones in my next lecture. Now, the PI of Kepler, the former science guy Kepler Vilbaruki, I understand he was here at NRAO, I guess, recently talking about this. And it's really funny because he will say that on the surface, Kepler is the most boring space telescope ever. Because it does the same thing every 6 seconds. It just takes a snapshot of 150,000 stars like the sun. So it's doing that over and over and over again. And downlink of data is an issue. So all that data doesn't get downlinked, but it gets binned together on board the spacecraft. And once a month, it gets downloaded to Earth in different time intervals. So what I'm going to do now is walk you through some of the data, because I want you to see what it looks like and how to find an exoplanet using the transit technique. So I'm going to explain this to you. Here is real data from Kepler. The planet's called Kepler 10. You know, you'd think in exoplanets we could be a little more creative with names of planets. But it was another thing people disagreed upon. Just the same people who actually had a Pluto issue. same governing body, they couldn't decide if you could just name it if you discovered it. So the planets actually end up getting named after their host star. So if you have Ursa Majoris, you get Ursa. If you have, say, Alpha, what do you think of a good one? Well, one is a catalog name, HG209458, after Henry Draper, who a long time ago cataloged bright stars. And so you call HG209458b, little b. You don't get to name it after your cat or something. So the Kepler stars, no one had named them before because they're so faint, no one had bothered cataloging them. So if Kepler finds a planet, the star gets named Kepler 10, and the planet will get named Kepler 10b. So this is just Kepler 10 after the star, which might get a capital A, just to make it a little more complex. So you're seeing here is time and days. This is 300 days worth of data. You see relative brightness. And look at this. Look how many decimal places are here. This is basically 5 parts in 10,000. Right, so this is a few parts in 10,000. What we're seeing here is the star constant brightness of time. There's fluctuation here just based on, we call it shot noise, but it's just based on star flux and also based on the instrument. And to find a transiting planet, it's really the computer that does this, but we can do this by eye. You're supposed to look for patterns in the data. So take a look at this for a minute and see if you see anything that looks like a pattern or might look like a transiting planet in the data. See anything? Someone's nodding, but I know that's the astronomer. Okay, the astronomers are nodding. The other thing is look at what you see. The first thing you can see that's clear are these big black spots. That's when no data is taken. And these are times when the spacecraft went into safe mode. If there's a problem, it shuts down for a while until engineers can figure out what's wrong with it and communicate to fix it and then turn it back on. There's other times that once a month when Kepler has to turn and downlink data to Earth, it actually doesn't take data then. There's other times when it has to it has to reorient itself so the solar panels are always pointing towards the sun. So a lot of things happen there. So these aren't the transits. And okay, let's just give it some thought for a second. The slides are made so that it gives you the answer on the next slide. So there's one transit. You can see the blue lines are showing you the transit. Now this is a time scale of days, and the transit will last for hours. Okay, so it looks all kind of scrunched up. And that's one transit of a period of about 45 days. Okay, so now we're going to zoom in on this region. So first of all, did everybody see this in the data? Does everyone agree that looks like a repeating pattern? I'll have to look at for an English professor or major to make sure. Okay. All right, now it's going to be a little harder, okay? So we're going to zoom in here on a shorter time of data. Now this is only about 10 days worth of data. And this blue line is showing you the transit from before. This data, we just call it noisy. It's not perfect because it's mostly instrumental effects. You can't make a perfect measurement. The question is now, do you see another transit in the data? Some people are nodding yes, but I bet it's someone who works with data. Okay, some people look a little uncertain, some people think they see it. Okay, again, we have the little like symbol. And if you want to ask me the question Q&A, what are the sources of noise, I can go through those for people who are more technically oriented. But look, there you go. That doesn't look so great, actually. It's definitely repeating, because the way that Kepler finds data, the way that Kepler finds planets is not really by eye looking for those patterns. It's actually the computer that will put the data together. We call it bin the data, but fold it over and see the repeating pattern all together in a way that makes the signal stronger. That's what this figure is here on the right. If we took that data and phased it now, the relative brightness, it all actually comes together. So that's a little confusing how I went from one to the other. Let me try to explain that one more time. So you have this data here. What if I took each of these and folded it on top of each other? So I took the data and instead of putting it in from 1 to 10 days, I just folded it on the period of 0.84 days and repeated it that way. You can put the signal together and get a much stronger signal. But even if that part didn't make sense, I'm hoping that everybody sees a drop here and agrees that that red line is a good fit to the data. This little drop, look how tiny it is. This planet is really small. Planet Kepler 10b is 1.4 radii, and the cartoon on the left is showing you planet way in front of the star and what it looks like. So now I'm going to move on to tell you a bit about this planet, Kepler 10b. And this particular planet also has a mass measurement with a different technique, rate of velocity technique, so we know the density of this planet. And this planet now, Kepler 10b, was announced a few months ago. It's known to be the smallest exoplanet discovered to date and the first unquestionably rocky planet outside our solar system. This planet orbits a star very much like our own sun, but it's older, and it has a distance of about 560 light years away. Now,